we can use any type of edge trigger, that is positive or negative edge trigger flip-flop. Now operation. Okay, the data, suppose we would like to store 1010. So these bits are connected, these all the 4 bits are connected to each D flip-flop. For storing of that 1010 data, we require 4 flip-flops. Just like here, we have shown 4 flip-flops, XF0, 1, 2, 3. So 4 inputs, B0, B1, B2, B3 are connected to the 4 inputs of the flip-flop. And 4 outputs are here Q0, Q1, Q2, Q3. So B0, B1, B2, B3, 10, 10 we have given, and when we apply the clock pulse, then that will come at the output. So what are the different types of register? Now, depending on the mode of operation, the register are of basically 4 types. One is serial in, serial out. Another is serial in, parallel out. Parallel in, parallel in, serial out. Parallel in, parallel out. In case of serial in, serial out, shift register maybe two types. One is shift right operation, another is shift left operation. In case of shift right operation, data will be shifted from left side to the right side by application of one clock pulse. Similarly, shift left, the data will be shifted by 1 bit from right to left by application of one clock pulse. Now, this is a summary of different 4 types of flip-flops. First, here is shown serial in, serial out, shift register. Means here we consider shift right. So data entered from the left side, and one by one when you apply the clock pulse, one data is entered per clock pulse. Similarly, shift serial in, serial out, shift left operation, data is shifted from right to the left by 1 bit or by 1 position per clock pulse. Serial in, parallel out. Data are here entered serially, but outputs are parallel from the 4 flip-flops. So after application of 4 clock pulse, all the data outputs will simultaneously appear at the output port. Last one, parallel in, serial out. So here data are entered parallelly, but output are taken serially one by one after application of 4 clock pulse. Now serial in, serial out. Here we consider left shift operation. That is, data is shifted from right side to the left side. So here all the flip-flops are connected serially. Output of one flip-flop is connected to the input like this way. 4 flip-flops are connected. We would like to store a 4-bit data 1010. So here for shift left operation, data to be entered from MSB side. So first data to be entered, this first one, then this one, then third, and then LSB. And accordingly, the data will be shifted from right side to the left side. Basically, this is all our D flip-flop. We know that a D flip-flop function output Qn plus 1 is equal to D after application of clock pulse. So output is same as input when you apply the clock pulse. So here, one example we consider 1111. So when first data is given here, so after application of the clock pulse, that data will be from here, and the 0 will be shifted here, and that 0 will be shifted here, and this 0 will be shifted at the final output. Next, when we apply the second bit, that means the second bit, second one, that after application of the clock pulse, that data will come at the Q0. The Q01 will transfer to Q1, Q10 will transfer to Q2, and Q20 will transfer to Q3. So like this way, if we apply another one, the third one, then output will be 0, 0, 1, 1, 1. And finally, when you apply another bit and application of clock pulse, then 4 output will get at the 4th output port of the flip-flop. So this is a summary of shift left operation. So first, initially we assume that all the flip-flops are reset position 0, 0, 0, 0. Then first data is entered, that Q0 will be 1, and then another one is given, to the Q0, and the Q0 data will transfer to Q1. Another clock pulse we apply after application of another bit 1, so data will be transferred to the left side, and after application of the 4 clock pulse, all the outputs Q1, Q2, Q3, Q3 will be 111. Now, right shift operation. So similar way, just reverse thing we have considered here. Data are entered from the left side. Output Q3 act as input for the flip flop 2. Q2 will act as a flip flop input of flip flop 1, and Q1 will act as a Q1 output act as input for the flip flop 0. So here data is entered from D in. Here the LSB data will be first entered. In case of left shift operation, NSB data enter first, but in case of right shift operation, LSB data will be entered first, and accordingly data will be entered and clock pulse will applied. So here one example is given. Suppose we would like to enter 10102 to store in the 4-bit shift register. So first 1 will be given to the input port, and we will apply to clock pulse, then that one will store at the pass bit. Next one we apply and clock pulse to apply, then that first one transfer here, second one will transfer at this first position. Then 0 will be applied and clock pulse apply 011. Then the MSB bit 1 is applied, that 1010. Next, if we apply the clock pulse, then that data will shift, and the last LSB data will be taken out. Serial in, parallel out. So here this type of shift register can be used as a serial to parallel converter. So data enters serially, but output will be taken parallel. So here, so if we apply the data just like shift register, either right shift or left shift operation, serial in, serial out case. So same way we can apply the data to the, here basically right shift operation is considered. So data is entered from here, LSB data first enter, then accordingly second LSB, accordingly that MSB will enter, and we will apply the clock pulse. So what will happen? All the bit will transfer, and after applying the 4 clock pulse, all the data will come here at Q0, Q1, Q2, Q3. So here, if we apply so 4 clock pulse, then after applying the 4 clock pulse, the 4 data will taken from this final output. Parallel in, serial output. So in this operation, the data are entered parallelly. So after application of 1 clock pulse, all the data will be stored in the 4 flip flops. There are two modes basically here. First one is we have to load the data, we store the data, and then shift the data for taken out. So first, all the after application of 1 clock pulse, all the data will be loaded to the register, and another 4 clock pulse is required to unload or to shift the data from this register. So this is the circuit diagram for parallel in, serial out. So first we have to enter the data parallelly. So this red like B0, B1, B2, B3 are the parallel input. So when there are two operations we have to consider. On control line we have select, we have considered shift or load with a NOT gate. We have connected like this 1, 2, 3, 4, 5, 6 is AND gate, and another OR gate we have applied. Such that the data entered parallelly, but after entering the data to the flip flop, the data will be shifted from left to right side. So here, when we consider shift or that mode is low, then what will happen if it is low? Then this NOT gate output is 1, that means AND gate 2, 4, and 6. This AND gate will be enabled, and as it is 0, so AND gate 1, 3, and 5 will be disabled. Whatever the data is here, that will be always 0 because this one input is 0. But here, if we see the B1 and this one is AND operation. So AND operation of these two will come here. So whatever the data B1 we have applied, that will come at the B1 input. Similarly, B2 data will come at the B2 input. B3 data will come at the D3. So as well as B0 input directly come to the B0 input. Now after that, after that if we apply the clock pulse, all the data, that is B0 will come at Q0, B1 data will come at Q1, B2 data will come at Q2, and B3 data will come out at Q3. Now for the serial out, what we have to do, already the B3 data is at the output. Now if to get the data shifted from left to right, what we have to do, this shift load that control input as high. So as now it is high, so and 2, 4 and 6, these 3 and get will be visible during that time, and get 1, 3 and 5 will be enabled. So whatever the data at Q0, that will come by and get an order to D1. Similarly, what is Q1, that will come to D2. What is Q2, that will come at D3. So when we apply the clock pulse, then what will happen? This Q0 is here, so that data will come at Q1. So shifted by 1 bit. Similarly, what the data at Q2, that will come at, sorry, what is the data at D2, that will come at Q2. Similarly, D3 will shifted to Q3. Similarly, again if we apply the clock pulse, then that data will shifted to the right by another 1 bit, like this way data will be shifted. So here the data entered parallelly, but the data are taken out serially from this output. Parallel in, parallel out. So this is basically a buffer register. In this operation, only one clock pulse is required to load all the flip-flops as well as to take an output. So here B0, B1, B2, B0, B1, B2, B3 are the inputs, and Q0, Q1, Q2, Q3 are the outputs. So when we apply the, so here apply the input B0, B1, B2, B3, and when we apply the clock pulse, then all the data B0 will come at Q0, B1 will come at Q1, B2 will come at Q2, B3 will come to Q3. So only here, only one clock pulse is required to load the data in the register. Now, so far what we have discussed, the unidirectional shift register, either to the left shift or to the right shift. Now here we consider 4-bit bidirectional shift register. That means a single circuit can be shifted by 1 bit to the left side or to the right side. Here a control line is considered. So just like parallel in serial out like this way, a control line is considered, and that control line directly connected to pin number and get 1, 3 and 5, and by NOT operation and get 2, 4, 6 and 8. So what is happening here? When that M is 1, that means control line is 1. That means 1, 3, 5, 7. These and gets are enabled, and as M is 1, so its complement will be 0. So and get 2, 4, 6 and 8 are disabled. So during that time, if we enter the data from here, from another input of AND gate, then this input will come via AND gate 1 and OR gate to the D3 input. And if we apply the clock pulse, what will happen? That data, D3 data will come at Q3, and this Q3 will come to D2 via AND gate 3 and OR gate and OR gate. So if we again apply the clock pulse, and simultaneously if we apply the input from here, so that data will come, D3 will come to Q3, and that Q3 to D2 to the Q2, and that Q2 will come at D1, and that data D1 after application clock pulse will come at Q1, and that Q1 will after the input D0, and after application clock pulse we get Q0 output. So here the data are shifted right. Now to shift the data to the left, what you have to consider, M is equal to 0 if you consider, then this red line means AND gate 1, 3, 5 and 7 will be disabled, and by using NOT gate, that control line connected to AND gate 2, 4, 6 and 8. So 2, 4, 6, 8, these AND gates are enabled. So and get 8 and or get to the D0 input of first flip-flop here FF0. And when you apply the clock pulse, that data will go to the input of pin number 6, and that will act as the input of D1 of flip-flop 1. So when you apply another clock pulse, that D1 data will go to Q1, and that Q1 data now goes through this part because it is and get 7 is 0, so there is no effect here. So this Q1 data will go through and get 4 and or get to D1. So when you apply the clock pulse, then D2 will taken out from the Q2, and that Q2 will act as the input for D3, and when you apply the clock pulse again, then that will come at Q3. So the data are shifting from right side to the left side. So this type of shift register is called shift left shift. So both type of shifting, left shift as well as right shift, can be performed using a single circuit with a control line. Now 4-bit universal shift register. So here, in the previous slide, we have seen the bidirectional shift register, left side, right side. So to perform the two operations, we use a control line. If we use two control line, then we can perform 4 different operations using the same circuit. So here we consider two select line, two control line. Using two control line, possible combinations are 4. So 4 different operations we can perform using a single circuit. So here we assume when that two control line or more control lines are 0, 0, no change. So whatever the outputs are there, that will cyclically move, and again at the output same we get. When you consider 0, 1 input, then shift right operation will perform. When you consider 1, 0, shift left operation will perform. When you consider 1, 1, then parallel load, means parallel in, parallel out, that operation can perform. So this is the circuit diagram. Here to consider the 4 operation, here we use a 4:1 marks for that two select line S1, S0 we consider just like previous slide. So there are two select line, a 4:1 marks means 4 input, 1 output line, and these are basically 4 D flip flops. So initially all the flip flops are clear, so 0 output. So whatever the data are there, here we assume 0, 0, 0, 0. Now when we consider 0, 0, these select lines, then what will happen? The multiplexer D0 data, what is mentioned as 0 of all the multiplexer, will be transferred to the output. So here this 0, 0 means whatever the data at the D0, that will transfer here. Whatever the D0, the second multiplexer, that will be taken as output, similarly for the third and fourth multiplexer. So what will happen? So D0 input is connected from the output of this A4. So A4 is coming here and coming to the D0 input, and that acts as the output. And that output again connected to the D input. So when clock pulse will appear, so that will again at the output we get. So whatever the output is here, that is cyclically rotate and come back to the original source. So there is no change of output. Similarly for the A3, A2 and A1 will happen. Now when we consider 0, 1, S1 is 0, 0, 1. So shift right operation will perform. So 0, 1 means D0 data will be selected. So whatever the data at D0, 1, that will be taken as output for the all flip flops. Sorry, all multiplexers. So here serial input for the shift right operation is taken from here. So D0 or D1 data will be taken as the input for the serial input for the shift right. So when D0, whatever the data is here, that data will come here, and when you apply the clock pulse, then that will come at the output A4, and that A4 is connected as well as to the D1 data input of the second multiplexer. Here it is also connected with the D0 because it is not operating, because only the line 1 will operating. So this is not operating condition. So this data will connected to the D1 data of the multiplexer 2. So that will come here, and that data when you apply the clock pulse will come here. So whatever the data here after application of the second clock pulse, that will come here, and that data is connected again to D1 of the third multiplexer. So again it is coming here. So when you apply the third clock pulse, that data will come here. After application of the fourth clock pulse, that data will come here. So the data are shifting from A4 to A3 to A2 to A1. So data is shifted towards right. Because of that, it is called shift right operation. Now to consider the shift left operation, the data enter from the D2 input of the multiplexer from the right side of the multiplexer. So here D2 is active as we consider 1 0. So that whatever the data is entered from this serial input, that will come here, and that acts the input for the D flip flop. So when you apply the clock pulse, this input will come to the output, and that output is fed to D2 input of the second multiplexer, and that is taken out here. When you apply the second clock pulse, you get the output here at A2. So whatever the output A1 at the first clock pulse, after application of first clock pulse, that will come at A2, and that is now connected to again D2 of the third multiplexer. So that is coming here and act as the input of the third D flip flop. So after application of the third flip flop, third clock pulse, we get the output at A3. So after application of third clock pulse, what will happen? The data what is here at A1 will shift it to A2, and then at A3. After application of next clock pulse, it will come at A4. So data are shifted from right side to the left side. So data shifting from right to left means here the left shift operation will perform. Now last one is 1 1. When the select lines are 1 1, then the D3 of all the multiplexer will be active. So whatever the inputs are D3 of all the multiplexer, I1, I2, I2 and I3, I4, that will taken out from the multiplexer of the 4 multiplexers, and that acts as the input for the all D flip flop. So when you apply the clock pulse, this D will taken as output. So whatever the I4 data will come at A4, I3 data will come at A3, I2 data will come at A2, and I1 data will taken as A1. So here data are entered parallelly and taken as parallel output. So parallel output operation can also be performed here. So what are the applications of shift register? For temporary storing the data, you can use the shift register as a delay line, because one flip flop give a particular delay of one clock pulse. So we can use a register as a delay line. We can design one special type of counter using the shift register. After this slide, we will discuss this one. And obviously, parallel to serial and serial to parallel converter, as we can use shift register. Now, shift register counters. Shift register may be arranged to form different types of counters. So in this case, it is like different of normal counters, synchronous asynchronous counter. Here, feedback is given from last flip flop to the first flip flop. Now, depending upon the feedback, from where we take the feedback, from Q or QR, from that concept, the shift register counters of two types. One is called ring counter, another is called Johnson counter. Ring counter. See here, just Q of the last flip flop is connected to the input of the first flip flop, just like a ring. Because of that, it is called ring counter. And here, special feature is that the clear of the first three flip flop are connected to this line, and the same line is connected here with the preset. So first three flip flop configurations are same, and last one flip flop is reverse one. And here at the first, this clear input of the first three or preset input the last flip flop is first given low and then high, and the preset of the first three and the clear of the last one given always high. So we know that if preset is 0 and clear is 1, then output will be 1. If preset is 1, clear is 0, then output will be 0. So if we give a low input to the preset input of the last flip flop, and high high input to the clear input, then what we get? At this output we get P is equal to 1 and others output will be 0. So outputs will be 0, 0, 0. Whatever the clock pulse meter, without applying clock pulse, we get the final output here 1 and other keys are 0. And these output will act as the input for the fast flip flop. So when you apply the clock pulse, what will happen? So when you apply the clock pulse, this one transfer from the input to the output, and here 0 will transfer from here Q3 to Q2, and the 0 of Q2 will transfer to Q1, and that Q1 will transfer to Q0. So this 0 again transfer to, so here it will be 0, here it will be 1. So 1 will be shifted by 1 bit after application the clock pulse. So this is the truth table of that ring counter. So with the whatever the condition of the clock pulse, when we consider that ORI means overwriting input, whatever the inputs are there here, it will override, because of that it will be written as ORI, and here it will be given as 1. So the Q0 data will be 1. After application of clock pulse, Q1 will be 1, all other 0. After application of the next clock pulse, Q2 will be 1, and after application next clock pulse, Q3 will be 1. Again it will repeat if we apply the clock pulse, and Q0 is 1. So this is a timing diagram for the ring counter. So 1 will be shifted by 1 bit. So after applying the fourth clock pulse, again it will 1. Johnson counter, what this is called also twist tail ring counter. It is similar like that ring counter, but output in output bar, Q bar acts as the input for the fast flip. And here all the clears are same, all the presets are same, and it is connected to 1. That means it is acting as a normal flip flop. That means all the flip flop outputs are 0. As all the flip flop outputs are 0, so Q bar will be 1. So that Q bar is connected to the first flip flop input. So after application of clock pulse, what will happen? It will be 1. QA will be 1. QB will be 0. QC is equal to 0, and QE is equal to 0. Till it is 0, so Q bar is 1. So when you apply another clock pulse, this one QA will transfer to QB, and this is also 1. So that will also transfer to QA. So what is the truth table? So when you apply the first clock pulse, QA is 1. When you apply the second clock pulse, QA, both are 1. When you apply the next third clock pulse, QA, QB, QC is 1. When you apply the fourth clock pulse, QA, QB, QC, QE is 1. If we apply another clock pulse, then as QE is 1, so QE bar will be 0. Because of that, the QA output will be 0, 1, 1, 1, and 0, 0, 1, 1, and 0, 0, 0, 1. I think from this truth table you can easily draw the timing diagram. So this is the all about shift register. If you have any question, you can mail me or WhatsApp me. Thank you.